Think back to the decision you just made a few seconds ago when you decided to click on this video. You might think that decision happened right then, a conscious choice made by the thinking and aware part of your mind. What if I told you, though, that your brain had already made that decision before you became consciously aware of it? That the sensation of deciding is actually just an afterthought. In today's episode, we're going to look at the latest breakthroughs in the study of human and machine minds and answer the question, just how different are they really? I'm Evan Goldstein. I'm a licensed professional engineer and a data scientist. I'm building the AI Capitalist channel to talk to the leaders and the thinkers, like you, about navigating this new world of intelligent machines. Now, with the extraordinary machinery in the human brain, there exists a fascinating division between what we consciously experience and the vast universe of unconscious processing happening beneath the surface. Like an iceberg, the conscious mind represents only a small fraction of our brain's total activity. Today, we're standing at a remarkable crossroads in our understanding of how the human brain processes information. Recent discoveries in neuroscience, combined with advances in artificial intelligence, have begun to reveal something profound about the nature of our decision-making process. They suggest that our brains operate primarily as prediction machines, constantly anticipating what might come next, often before we're consciously aware of it. How does our brain really process information and make decisions? And even more importantly, what role does our conscious awareness play in this process? The answer, as we're about to discover, challenges some of our most basic assumptions about the nature of human consciousness and decision-making. In the next few minutes, we'll explore groundbreaking research that suggests our conscious experience might be more of an observer than a controller, a passenger rather than a driver in the vehicle of our mind. And through this journey, we might just discover something remarkable about the nature of human consciousness itself. Consider for a moment a simple experiment performed by Goldstein and colleagues in the study referenced below. No relation to this Goldstein. They have 5 human subjects listen to their podcasts while measuring their brain activity using electrocorticography, which is direct recordings from the surface of the brains. What they found was extraordinary. Across more than 1,300 electrode readings, they could detect specific patterns of neural activity predicting words before they were actually heard. But they didn't stop there. In a parallel behavioral experiment, they had 300 participants predict upcoming words in the story, one word at a time. The results were remarkable. When given sufficient context, human participants could predict the next word with surprising accuracy, about 28% of the time. This might not sound impressive until you consider that a random guessing would yield less than 6% accuracy, given the enormous variability of possible words. Let me share a simple demonstration. When I say Mary had a little, your brain likely completed that sentence with lamb before I could say it. But this is just the surface of a much deeper phenomenon. Even more fascinating was the timing. The brain's predictive signals appeared up to 800 milliseconds before the word was actually spoken. So think about that. Nearly a full second before you hear a word, your brain is already making educated guesses about what it might be. It's auto-completing the sentences. But here's where it gets even more remarkable. When researchers compared the patterns of activity in human brains with the internal states of artificial neural networks, they found striking similarities. The researchers compared these human predictions with those made by GPT-2 and found a striking correlation. About 49% of the times, humans and AI made the same predictions. This wasn't just happening in a few isolated brain regions. The researchers found this predictive activity across multiple areas of the brain, particularly in regions known to be involved in language processing. The brain's prediction system operates across multiple timescales simultaneously. While one part of your brain might be predicting the next word, other regions are anticipating entire concepts and ideas that might follow. Now, this hierarchical system spans from milliseconds to seconds, creating a cascade of predictions that help us understand and navigate our world. Evidence suggests that this predictive processing isn't just a feature of language comprehension. It's a fundamental principle of how our brains work, from anticipating physical movements to understanding complex social situations, Our brains are constantly running predictive models of the world around us. This discovery raises profound questions about the nature of intelligence itself. Are prediction and error correction the fundamental building blocks of understanding? And if so, what does this tell us about the relationship between human and artificial intelligence? And if you feel that this episode is of value to you, I would appreciate it if you push the like button. Pushing like lets me know I'm making content that you want to see, and it spreads that content to others. So thank you for supporting the channel. But in science, extraordinary claims require extraordinary evidence. And in 2024, researchers Antonello and Huth presented a compelling counterargument that challenges our interpretation of these remarkable findings, using techniques to test these ideas directly. So let's begin with a fundamental question. How do computers understand words? Unlike humans, computers can't inherently understand meaning. They need to convert words into numbers. Now, this conversion creates what we call a language representation. Think of it like giving each word a unique set of coordinates in space, where similar words are placed closer together. For example, dog and cat might be closer together than dog and refrigerator, because dogs and cats are both animals. The simplest form is called a word embedding system. It's like a dictionary where each word gets a fixed set of numbers that never changes. More complex systems like GPT-2 create representations that change based on context, just like how the meaning of bank changes depending on whether we're talking about money or rivers. Human experimental subjects were told to listen to the podcasts while being brain scanned. The researchers wanted to see how the human brain processes natural language in real time. While subjects listened, an MRI scanner measured blood flow in their brains, showing which brain regions were active during language processing. Here's where it gets interesting. The researchers took 97 different ways that AI systems represent language, from simple word embeddings to complex language models. And they tried to use each one to predict the brain activity that they observed. This process is termed constructing encoding models. They were testing which AI representation best matched the patterns they saw in the brain. They even used a model that was designed to translate English to German. The German translation example, while it seems a little odd since the subjects didn't speak German, it makes a crucial point. They found that an AI system designed to translate English to German could predict brain activity almost as well as systems designed to predict the next words. And this suggests that the similarities that we see between brains and AI might not be about prediction at all. They might just be about understanding language in general. The researchers demonstrated this through 3 parallel analyses. First, they showed the correlation between how well different AI systems predict next words and how well they predict brain activity. And they found a correlation of 84.7%. But crucially, they then showed that general transfer performance, or how well these systems perform on any language task, had an even higher correlation of 86.4%. And even more telling, the ability to predict German translations showed robust correlation of 78%, despite none of the subjects actually speaking German. They then performed a more detailed analysis looking at different layers within GPT-2, using a variance partitioning, which is a statistical technique that separates out unique contributions of different factors. They made a striking discovery. The intermediate layers of the model, which aren't optimized for prediction, actually explained more variance in brain activity than the final layers that are specifically tuned for next word prediction. Think of GPT-2 like a series of filters that language passes through, similar to water flowing through different layers of sand and rock. Each layer processes the languages in a different way, with 12 layers in total. The final layer is specifically designed to be best at predicting what word comes next. Now, the surprising discovery was that when the researchers compared brain activity to these different layers, they found something unexpected. The 9th layer, not the 12th layer, matched brain activity patterns the best. This is like finding out that water filtered through just 9 layers of sand is cleaner spring water than when it's going through all 12 layers. Even more interesting, anything the final layer could tell us about brain activity, the 9th layer could tell us just as well. And then some. It's like having 2 weather forecasters, one who can predict rain and temperature and another who can predict only rain. Even though they can both predict rain, we'd say the first forecaster is more useful to us. To make sure this wasn't just a coincidence, the researchers did the scientific equivalent of a double and triple checking of their work. They looked at different brain regions, different subjects, and used various statistical tools to verify their findings. Now here's the big picture. Imagine you have two people who both arrived at the same destination, one by car and one by bicycle. Just because they ended up in the same place doesn't mean that they got there the same way. Similarly, just because AI systems and human brains show similar patterns when they're processing through language, that doesn't mean that they're using the same methods to understand language. This suggests that certain patterns in language processing might emerge naturally, regardless of how a system is designed. Just like how both birds and airplanes ended up with wings, even though they developed it in completely different ways. The implications of these findings for our understanding of consciousness are profound. If our brains are making decisions before we are consciously aware of them, what role does consciousness actually play? Let's examine what these studies suggest about the nature of choice itself. When we believe that we're making a decision, we're actually becoming aware of a choice that our brain has already made, like reading a script rather than writing one. This resembles how modern AI language models like GPT process information. They don't consciously deliberate about their next word, they make predictions based on patterns that they've learned from the past. Our conscious experience may be more similar to this than we've previously imagined. What does it mean for our understanding of consciousness? Rather than being the author of our thoughts and decisions, consciousness might be more like a narrator, telling us the story of what our brain has already decided to do. Think of it like watching a live sports broadcast with a slight delay. The action has already happened by the time we see it, but our experience feels immediate and real. Similarly, our conscious awareness might be operating on a slight delay from our brain's actual decision-making processes. This doesn't mean that our consciousness is unimportant. Instead, it suggests that consciousness plays a different role than we assumed, perhaps helping us learn from experiences and adjust future behavior rather than controlling our immediate decisions. Some find these ideas unsettling. After all, if our conscious mind isn't in direct control, what does that mean for concepts like free will? But perhaps we're asking the wrong question. Maybe what makes us human isn't the illusion of conscious control, but rather our ability to learn, to adapt, and to shape our future responses through reflection on our experiences. What we're discovering about human cognition and artificial intelligence suggests a remarkable convergence. Both systems appear to operate on similar principles: prediction, pattern recognition, and hierarchical processing. However, the key difference may lie in how these processes are carried out. Consider the three key insights from our studies. Number one, both brains and AI systems predict future inputs. Both operate hierarchically with multiple levels of processing, and both show similar patterns of activity when processing language. But here's the crucial distinction. While AI systems were deliberately engineered this way, our brains evolved these mechanisms naturally. This suggests that there might be fundamental principles of intelligent information processing rather than just one possible approach. For AI development, this indicates that we may be on a promising path. The similarities between neural networks and brain function aren't just superficial, they reflect deep computational principles. However, we have to be cautious about overinterpreting these similarities. Just as birds and airplanes both have wings and fly, they still do so very differently. AI and human brains may achieve similar results through different means. Now, what does this mean for humanity? We're beginning to understand that our conscious experience, our sense of being in control, might be more like a useful interface than a control center. It doesn't diminish the human experience. It helps us better understand how we interact with the world. The future of both human and artificial intelligence research likely lies in better understanding these predictive processes. As we continue to explore those parallels, we may find ourselves not just building better AI, but gaining a deeper insight into what makes us human.